Hello, everyone. Welcome to the Recurrent ETDS seminar. And today we have the pleasure of having Nicanor tell us about slow entropy of some skew products. So just a small thing, I saw Nicanor last year in Marseille, and I remember he was this PhD student, and that back then, and every talk he had a few questions. So I'm very glad that I'm on the other end for his talk this time. Anyways, with that, please over to you, Nicanor.
Thank you. Well, first, thanks for the invitation to speak here. Second, please make many questions. So, well, I will talk about slow entropy of some skew products. This is based on this preprint, which is on Archive. And this work was mostly guided by Adam Kanigowski, so thanks to him. So I will start. So I mentioned that in this talk, all systems have discrete time. So the integers are the naturals, no flows. And a measurable dynamical system means a measure preserving transformation on a probability space. And a topological dynamical system is a continuous transformation on a compact metric space. And often they will be invertible, but not necessarily. So what is this talk about? It is about a class of skew products that I will define more precisely soon. And this construction can be done both for measurable systems and continuous systems or topological systems. So we will be interested in the complexity of these systems in the sense of entropy and related concepts. And well, we have this natural problem, which is that how can we distinguish two skew products that have the same base? So we have S times T1 and S times T2, and we may want to distinguish these two dynamical systems, which could be a very easy question depending on the situation, or could be a difficult question that requires complicates things. So, well, this question or this problem is well studied for measure preserving systems. There are some results. And here we studied for topological systems. And we propose a solution based on slow entropy, which is an invariant introduced by Katok and Tuveno, which I will define later. So I will informally talk about the T inverse system. So you take your favorite measure preserving invertible transformation T on a probability space, and then you apply randomly T and T inverse. That is the reason of the notation. So you flip a coin, and depending on what happens with the coin, you apply T or the inverse of T. So for instance, if your favorite transformation is a rotation, this goes as follows. You have the space and you have a point, and to compute its image, you flip your coin, and your coin may tell you apply T. Then you do the same. You flip a coin, and the coin may tell you apply T. And then you flip a coin, and maybe the coin will tell you apply the inverse of T. So your point went backwards. And then, well, you can iterate this infinitely. One way to formalize this is to take the space, which is the product of bi-infinite sequences, which represent sequences of coin flips times your original space. And this transformation, so you send a sequence to the shift of this sequence, and you send a point x in your circle to t, which is a rotation, power something of t. So here this will be 1 or -1 depending on the first coordinate of y. So when you iterate this many times, this will here you will apply t to the 1 or -1 according to the sequence of coin flips that is indicated in the sequence y that lives in this space. So a slightly more formal definition is that this system is a skew product of the Bernoulli shift action on this space of sequences with the uniform measure. And in the fiber, you take any invertible measure preserving system and the new transformation, which is denoted like this. Oh, here there's a typo, it should be the product space. Well, the new transformation acts on the product space with this expression, which is the same from before, but now T is an arbitrary invertible transformation. So why people like this system? One reason is that in 1982, Calico proved that when you take T, like the fiber system, as a transformation with positive entropy, then this product is K, Kolmogorov, but it's not Bernoulli. And at some point previously, it was conjectured that this property implies this other property. So it was like the first natural example having the property of K, but not Bernoulli. So, well, we have this collection of systems, and it arises the question of distinguishing them. So how can we distinguish these systems? One interesting thing that happens is that the entropy of the fiber system disappears in the sense that all these systems have the same entropy. So for any choice of a fiber system T here that we take, if we compute the measured theoretic entropy, we get the entropy of the shift, which is logarithm of 2, and this happens, well, one way to prove this is with Abramov and Rocklin's entropy formula, which says that the entropy of a skew product is the entropy of the base plus an integral, which, well, one can prove that in this case is always 0. So entropy doesn't tell us much. So then we can ask if the entropy of the fiber, like the entropy of T, is an isomorphism invariant within this class of systems. So that means that when shift times T1 is isomorphic to shift times T2, then T1 and T2 have the same entropy. And it turns out that the answer is yes. So that tells us that when T1 and T2 have different entropy, then we have non-isomorphic systems. That is, and then that the entropy of the fiber is an invariant in this class of systems, which is very nice. And then, well, after we know that this is true, we of course want to know more things. So now I will define something called generalized T-inverse systems. And essentially, we just now take something general in the base instead of the Bernoulli shift on symbols 1 and -1. So these systems are skew products. And now in the base, we have an arbitrary measure preserving system. And now we take a cocycle, which is a measurable function from the space y to the integers. This is important. The fiber system is again an arbitrary invertible system. And the transformation is similar to the previous one. So we have this S times T system, which acts on the product space. One can prove that it preserves the product measure. And y goes to S of y, and x goes to t to the something of x. So this something previously was 1 or minus 1, now is tau of y. So the idea is that we take a point y, which lives in this system, and we look at its orbit by the transformation s. And at each point of that orbit, we apply this cocycle, which gives us a number. And that gives us a sequence of natural numbers, and that replaces the sequence of coin flips. So now instead we can, using this language, we can formalize the idea of apply randomly t to the 2 and t to the minus 5, taking choosing the cocycle to do that. And well, more other things. This is much more general. So then we can ask for which choices of an invertible system, no, for which choices of a measure preserving system in the base and a cocycle, is it true that the entropy of the fiber is an isomorphism invariant in this class of skew products? So we are asking for which choices of the base system we have the same property as before. So this is known to be true for the one-sided Bernoulli shift on symbols -1 and 1 with the uniform measure. So this is like, again, coin flips, but one-sided sequences instead of two-sided sequences. This was proved before. Then we have the same result, but for the two-sided Bernoulli shift. This is the theorem from before. And well, also here the cocycle, which previously I did not mention the cocycle, but it was the zero coordinate. So, and we have this more general result, which says that this is also true for a mixing subshift of finite type with a Gibbs measure and a cocycle satisfying a technical condition, which is, so this is more general, but it also happens that this technical condition, to my understanding, is not known to be verified for many choices of tau. So, I mean, in this paper, Austin writes that Michael Bromberg is working on proving that this condition is actually satisfied in many cases, but to my knowledge, this has not happened yet. So this is general, but at the same time, this condition, one needs to verify it. So on the other hand, there are no results of this kind with zero entropy systems on the base. So all the known cases, which were the ones from the previous slide, were for high complexity systems in the base. And maybe one would like to know what happens about this question for a more diverse class of systems, but it appears to be difficult. So since it is difficult, we ask what happens for topological systems, because well, one can reformulate this question for topological skew products, and it turns out that it's doable. So we propose a solution that works for a diverse class of transformations in the base and cocycles, and diverse in the sense that the same proof works for high complexity things and low complexity things. I mean, complexity in the sense of entropy. So positive entropy and zero entropy. So I will now talk about topological skew products. So we consider systems defined as follows. We take any subshift, we take a cocycle, which is a continuous function from the subshift to the integers. And then we take an invertible topological dynamical system, and we define this new transformation, which is now a continuous transformation on the product space, and which is defined by the same formula as before. So it, it's good to keep interpreting this tau as coin flips of something, and then we apply powers of t according to another process, which is here. So after we fix a subshift and a cocycle in the base, we consider this family of products where T ranges over all invertible topological dynamical systems. And we are broadly interested in find a way to distinguish them, and maybe more specifically determine if the entropy of the fiber is an invariant for topological conjugacy, or maybe instead of entropy, some entropy type invariance of the fiber. So, well, if one writes this way, it is maybe natural that, in a sense, this question is easier for topological systems because topological conjugacies are continuous functions and they preserve much more than isomorphisms, like for continuous systems. So intuition is as follows. So this problem that we are considering is interesting when the entropy of the fiber disappears, in the sense that the fiber does not contribute to the entropy of the whole system. Informally, one can write this as saying that if we count how many n epsilon Bowen balls we need to cover the space, this can be written as approximately the exponential of n times the entropy of S plus a contribution that depends on the entropy of T. And the fact that T does not contribute to the entropy of the whole system means that this function f is sublinear. So when we take logarithm of this and divide by n, this fn over n disappears. This is, let me say that this is informal because actually some things depend on epsilon here, but I think it's a good picture of what happens. So we want to capture the contribution of the entropy of T or the complexity of T in this relation. And let me use this notation. So the number of Bowen balls needed to cover the space will be denoted by this. So spanning of T and epsilon. And now I will define topological slow entropy, which, as I mentioned, is an invariant and that was introduced by Katog and Tuvenon. And it was introduced for measure preserving systems, but the definition adapts directly to continuous systems. So we need to take a family of sequences indexed by natural numbers and a positive parameter. And we need two things that so for each n, a n of t is a real function, and we want this to be monotone in t. That is a first condition. And the second condition is that if we fix the parameter t, then this sequence, an, tends to infinity. That's all we need. So maybe in other words, this is a sequence of monotone real functions, depending on if we fix n or if we fix t, but well. So this choice, we call it a scale, and then we compute the slow entropy of something with scale A. So for each family of sequences, we have a new invariant. This is a family of invariants. So the upper slow entropy of a topological system with scale A is defined as follows. So it is denoted like this number, which is defined as the limit of this new number, which depends on epsilon. So the upper slow entropy with scale A of t that depends on epsilon is defined as this quantity. So this looks a bit large, but let me try to explain what it means. So here we have a lim sub on n. So here we make n tend to infinity, and we compare this spanning number with an of t, which is a sequence in n. So we have two sequences in n, and we want to see which one grows faster. So if t is little, it may happen that this one, the spanning sequence, grows faster, and then this lim sub is positive or infinite. If t is large, like ideally what should happen is that for some large t, this sequence here, an of t, will grow faster than this one. And then the lim sub will be 0.
Nicanor,
So,
before you proceed, can you,
oh,
uh,
sorry. Yes.
yeah, can you just quickly remind me the definition of this spanning set T and epsilon one more time?
Yes.
So
Here.
it's just the number of n epsilon both. Ah, that's it. Needed to cover the space. The minimal number. Okay.
Yes. Um,
So if I'm looking at say a shift space, then it's just the number of words of length n for a appropriate epsilon, of course.
mhm. Yes, in
And
that case, one can like actually it is correct to forget about epsilon
right.
because for epsilons one gets the same and you're just comparing the language
Mhm.
with this sequence.
Right. And so now you're looking at the minimum t for which this is greater than 0.
Mhm.
Um, right. So if say my shift space is growing sub exponentially, then say it has quadratic growth, then if you had t square, sorry, n squared as your so what is a little confusing is you have two parameters here. One is this sub n, and then there's this t. And
Yes.
uh,
Maybe let me give an example. So if you have
yeah,
a subscript whose complexity function has quadratic complexity, so it grows like n squared,
hmm,
then one scale, which is like the good one, would be n to the t, n power t.
hmm,
And
hmm,
then when you
hmm,
do this thing, when you take here, let's say n to the 3, it will grow faster
hmm,
than the language. When you take n to the 1, it will grow slower and so on. So there is a threshold which is exactly at n to the 2.
uh-huh,
So this tells you that if you compute the upper slow entropy of that subshift with that scale,
hmm.
you get exactly 2, which is the exponent. So, um, for
Okay.
instance,
Hmm.
uh, yes, that is the idea. So if you have subshifts with polynomial complexity and you take the scale n to the t, then this
Mhm.
number will be the degree of the complexity in your subshift.
Uh-huh.
Does that maybe clarify things?
Yeah, it does. It does. Thanks.
So, okay. So some comments about the definition. One is that we can define lower slow entropy taking liminf instead of lim_sub in this definition. And it could happen that the upper and lower slow entropy are not equal, and this can happen when this complexity function n to the spanning number behaves differently along different subsequences. And also, if we take the scale exponential nt, then this invariant coincides with topological entropy. So in that sense, it is maybe a more general thing. Also, well, I say this, but whatever. So if we take this scale, people call this the polynomial scale, and with this scale, we obtain the so-called polynomial complexity or polynomial entropy of the system. And well, there are more scales. These are like two maybe canonical relevant scales, but there are actually too many scales because the definition of scale is very broad in a sense. Like many things can be a scale. The interesting thing is to see what scales are meaningful depending on your system or your class of systems. So, well, now I can state the main result. So the main result is that if we take a subshift and a continuous cocycle, then we can find a scale which is defined depending on this subshift with the property that if we take the skew product with some dynamical system T, then the slow entropy with scale A of this product system will be equal to the topological entropy of T. So there is a scale that captures the entropy of the fiber in this product, which is more or less what we wanted. And this is
Wait, you're
true.
not saying that your Y has zero entropy, or
Um, Not necessarily. It could have zero entropy, but it could also not necessarily have zero entropy, and this could still be true.
you would just multiply your scale with e to the power entropy of ys times whatever you would get otherwise. Okay, 1 minute. So you have
I think that maybe. I mean, I think it's good to think about it that way, but it's not literally that way. But I think what you had in mind was, for instance, if you have a subshift with positive entropy times a subshift with, let's say, polynomial complexity squared, then the scale should be something like the um, exponential of the entropy of the first subshift times the polynomial scale so that the exponential contributions cancel each other. And
right. That's what I had in mind.
so it is something like that, but not literally that. But
Uh-huh.
then later I will give a description of the scale. I think it should clarify that part.
Uh-huh. Actually, just another very quick and probably stupid question. This slow entropy is topological slow entropy is still an invariant, I guess, right?
Yes, it is an invariant for topological conjugacy. It
Uh,
is monotone by factors like entropy.
okay. Uh,
It is also monotone by embeddings like entropy. I
uh-huh.
mean, like amenable entropy.
I see. Um, hmm. Sorry, so I interrupted your flow.
No, it's fine. Well, I will continue. So this
Yeah.
result says,
Nicanor, before you proceed, just one short question. So right-hand side is the topological entropy, the regular exponential topological entropy of the fiber, right?
yes,
Okay. And
yes, yes.
there exists, you can find the scale such that this happens. So thanks. And please
Sorry, I
continue.
didn't understand the last
Okay.
part.
Now I think it's clarified now. Please continue.
Or, well, maybe you can write it like I have maybe audio problems or.
I think his question has been clarified. That's what he said.
Clarified. Yeah.
That's what
Please continue.
I roughly heard. Uh, so just as a actually it's, another sort of question. So one of the main reasons you were talking about this is you wanted to distinguish different systems, different extensions of y. But now, if your scale depends on y and well, also depends on tau, then wouldn't you be in?
So, well, it depends on like the class of systems one looks. So here, the class of systems that we look is we fix y, we fix tau,
And
and we
then we
look at
look at all the
the
transformations too.
products. Right. So two ranges over anything, more or less. And scale does not depend on this. So
Okay.
well,
Thanks a lot. Thanks a lot.
so well, this is true with some condition in tau that I will define later. And I mentioned that this is what we wanted in the sense that it shows that the entropy invariant, the entropy of the fiber is a conjugate invariant in the class of skew products of the form S times T, where we fixed S and tau beforehand, and we make T range over anything.
Can I ask another stupid question?
Yes, of course.
So suppose is it also possible that if you take something like y being circle rotations, well, okay, not circle rotations, but say being something like something with zero entropy, say, and now
Yes,
you
you can
take
take
your
like a subship copy of a circle rotation, like a Starmian or an extension.
right. And if T is like say the Bernoulli shift. But
Mhm.
all your systems are topological. Sorry.
Yes,
I was
but it can be
thinking.
a full shift, maybe, or a subshift.
Sorry. I was thinking measure theoretic. My question doesn't make sense in the
Okay.
topological category.
Okay, well, I will check some examples later that are more or less like what you mentioned, so I hope it will say something. So I want to explain a second statement. So this statement is similar to the previous one, but here, instead of trying to capture the entropy of the fiber, we capture the slow entropy of the fiber with some scale. So that is why it's called a relative version. So the statement is we take a subshift and a continuous cocycle, and now we have this extra condition, which is that it takes only values between -1, 0, and 1. And later, I think I will mention why this makes things much easier. So in this case, we can prove that for any scale B that you choose first, then there is another scale C that depends on B and also on Y and the cocycle, with the property that if you take any topological system T and you look at this Q product and you compute that slow entropy with scale C, you get something which is between the upper and lower entropies of T with scale B. So, well, these two may not be equal, but if they happen to be equal, so if the slow entropy of T with scale B, if the upper slow entropy coincides with the lower slow entropy, then these three things are equal. So this shows that if you choose a scale B, then the slow entropy with scale B is a conjugate invariant in this class, but you need to restrict to the class of T's with the property that the upper and the lower entropy coincide, which is not always true, but it's also like, it's not a horrible assumption. It occurs in many natural cases. Indeed, it's not so easy to make examples where this is false. So,
In particular, this theorem gives you the other theorem that you mentioned, the first theorem.
yes, right. So the other is more general because it doesn't have this condition in the cocycle. But if you have a cocycle that has this property, then both theorems tell you the same thing. So here you would take B as the exponential scale, and the exponential scale has the property that the lower and upper slow entropies coincide for all systems. So this is maybe in an informal way, there is this thing that in the typical formulation of topological entropy, there is a lim sup, but you can replace it with a liminf and you get the same thing. And that essentially means that with this scale, exponential scale, you have the same value for the upper and lower slow entropy. But for other scales, something can happen when you take lim sup and liminf. I mean, you may not get the same quantity, but since it is true for the exponential scale, like for typical entropy, yes, the previous result is in some cases a particular case of this one. So now I will try to explain what is this assumption that is in the theorem, which is that the cocycle tau needs to be lambda unbounded. So for notational simplicity, let's assume that the cocycle only depends on the zero coordinate of the configuration. This is not always true, but it makes writing the things easier. Otherwise, it's more ugly. So let's assume this for the sake of the exposition. So for a configuration little y in the subshift y, we have these ergodic sums, and we interpret these sums as a walk on the integers. So at each step, or walking entity computes the value of tau somewhere, and that may be +1 or -1, and that determines a step in some direction, right? So after we look at this sum as a walker, we can define the range as the set of points that our walker visits in n steps, formally this expression. So the condition that we need says that this range is large, often with some positive probability. But this does not refer to an invariant measure in the space. We did not fix one, we could fix one, but anyway, the condition refers to a proportion of words in the language of the subshift having some property. So we want that this number of this range is large, but in the sense of many words. So because we assumed that the cocycle only depends on the zero coordinate, to compute the range of a configuration, we actually don't need to all the configuration. This number depends only on the first n coordinates. So we can define the range for a word we can define range for words. So for a word of length n, we can compute its range up to n, like the same n. So the definition of the property is this: given a subshift and a cocycle that depends only on the zero coordinate of the configuration, we say that tau is lambda unbounded when for all parameters c in the naturals, this liminf is bigger than lambda. Now, what is here in the liminf? We are looking at the proportion of words of length n in the language of the subshift, such that the range is bigger than c. So we take n, we make n large, and we look at words of length n, and we want that many of these words have a range larger than c.
So, Nicanor, this is like some kind of transience of random walks, right? It's saying that, okay, there's no randomness in some sense, but you're taking all words of length n in your shift space, and then you want that your random walk has to Oh, wait, it's saying something slightly different. It's just saying that it will leave the ball of radius C. That's all it
Yeah.
is saying. It's not actually saying anything. Okay, I see.
I think it's
Yeah,
tricky.
it's much weaker than transients then. Sorry. Yeah, sorry.
So you fix C and a ball of, you can fix a ball of radius C, and then you can say that for most y's, the random walk escapes that ball, but that most refers to you cut the configurations to length n, and then you look at the um, proportion of words such that the configurations have that property.
So can we just think of this as you have your subshift ys and then you have this cocycle. You can just take the skew product for the non-compact space where you take y product z. And are you just asking that that random walk, sorry, that transformation that you get, that skew product that you get is recurrent or something of that sort? Is that what you're assuming? No, you're not assuming that either.
I am sincerely not sure.
Okay,
So, well,
okay. Anyways.
I tried to formulate this in other ways, but I did not find.
Could we for a minute go back to the definition of R and W and how it depends on tau, just for a minute? Okay, it's just the ergodic. Okay.
Oh, that is actually helpful.
Okay.
I got, I think, so R and Y is just the set of places where you visit. That's it.
Yes.
Right.
Maybe
So
if you don't mind, we can go to the picture because I think it should help. So here, let's think of the words 1, 1, minus 1. So we first apply t, this means 1, then another 1, and then minus 1. So we have the words of length 3, 1, 1, minus 1, and the range would be 0, 1, 2, and that's all. 0, 1, 2. Does this make sense? Or
Yeah, it does. It does. Right.
I think I may need to subtract like just the first element or something like this.
Sure.
But well, anyway, it's the set of places in the integers that the walker visits. That should like be the definitely true definition.
Yeah, you're absolutely right. I think whatever I was saying about mixing is definitely false. Yeah, but it's an interesting condition. Anyways, I've never seen this before.
Yes, well, maybe it can be formulated with the skew product with the non-compact like action on the integers, but I don't know. What I know is that if the range is unbounded for all y's, then this holds. So if you are on a subshift such that the ergodic sums of your cocycles are unbounded for all points, then you're fine, or you're happy this happens. But it does not need to be true. So for instance, if we take the full shift in symbols 1 and -1 with this cocycle, and then this property is also true. Well, I put a measure, but so here you can actually think about random walks, right? So it is not true that for all configurations here, the corresponding walker is unbounded, right? I mean, there are some sequences here such that if you look at the ergodic sums, they stay in a bounded place, but they are very small in measure, in this measure. So the statement that I measure one set of sequences here have the property that the ergodic sums are unbounded can be transformed, which is like a classical fact of random walks. In this case, can be transformed to a statement about a proportion of words having some property. So, well, if you erase the measure and you just look at this system, like as a topological subshift, then it also has this property. So, well, now I want to review some examples of choices of a subshift and a cocycle where this property is true, and then we have the results about entropy. So one class of examples is we take a minimal subshift and a cocycle tau, which is not a cobounder. So in this case, a theorem of Gottschalk and Hedlund ensures that the ergodic sums are unbounded for all configurations. So all the walkers do not stay in a finite region, and then we are happy in all these cases. The condition that we want holds. So one subcase of that case is this one. We can take, for instance, a Starmian subshift on symbols 0 and 1 with the cocycle, which is the 0 coordinate. And in this case, one thing that happens is that if you look at these skew products and you compute the entropy of the skew product, it will be equal to the entropy of your subshift, which is 0, plus a constant multiplied by the entropy of the fiber system. So this will be either the rotation angle or 1 minus the rotational angle, depending on how you define your Sturmian subshift. I mean, if one is the label of the arc of alpha or the other arc. But in any case, applying the main theorem is an overkill because you get the same conclusion that you could get with just computing topological entropy. But the conclusion is still non-trivial if you take T's with 0 entropy. So if you take T1 and T2 as systems with 0 entropy but different polynomial complexity, then these skew products both have 0 entropy and actually very low complexity, but this shows that one can distinguish them using slow entropy. Another interesting example is the subshift copy of the deterministic random walk. So we can choose an irrational number alpha and take the function on the circle that is 1 on one half and -1 on the other half. So, well, the ergodic sums of this function with the rotation are apparently very interesting, and there are many results about them, and many people is still interested in this. And in this case, we need to replace this system by a subshift copy because we want to make continuous skew products, and this function rho is not continuous, right? So one way is we take a point here, and then we take its orbit by the rotation, and that will give us a sequence of ones and minus ones. And then we can take the smallest subshift on those symbols containing that sequence. So it's just, we take the partition of two halves and we assign to it a subshift, and we label the elements as 1 and minus 1. I mean, we label the partitions. And here we take finally the cocycle, which on the subshift, the value, tau of a configuration is its zero coordinate. So it is 1 or minus 1. So here it happens that the topological entropy of a skew product is 0 for all choices of t. This is related to the fact that this function rho here has 0 mean, like 0 integral with respect to the Lebesgue measure, right? And then the same will be true on the subshift copy, which is uniquely ergodic, and it's, well, this subshift copy is uniquely ergodic and it's isomorphic to the irrational rotation. And the copy of the function rho, which is tau, also has 0 integral with respect to the new measure, and one can use that to prove that this is true. So, well, here we have an interesting class of zero-entropy systems. So entropy is not a useful invariant in this class, and it's reasonable to use other invariants. And this is also a subcase of the slide 2 slides ago. So this subshift is minimal, and this function is not a coboundary, and this was essentially proved by Kesten a lot of time ago, so it's classically true. So then we are happy and we can apply the main theorem, which tells us that there is a scale for slow entropy such that if we compute the slow entropy of the product, we recover the entropy of the fiber. And also the relative result, which allow us to compute the slow entropy of the fiber up to this detail that we must be careful with the upper slow entropy and lower slow entropy if the scale that we chose doesn't have the same value for t. And as a last example, well, maybe I should emphasize, so the motivation of these results is that we have these theorems for measure preserving systems that are, and the only theorems that are known are for high complexity systems in the base. So these two examples are with very low complexity systems in the base. So here S has 0 entropy. I wanted to say that. I claimed that the result works for a diverse class of systems S. So here are the 0 entropy ones. Now I want to mention a positive entropy example. So the last example is the full shift on symbols -1 and 1 with this cocycle, which is the 0 coordinate. So here, when we look at the skew products, they are like the topological version of the classical construction of T inverse system, like the associated topological system. So here one can prove that if one computes the topological entropy of the skew product of this system with something, then for the topological entropy, the fiber does make a contribution to the entropy of the skew product. So before, when we looked at this same object as a product of measure preserving systems with the product measure, and we compute the measured theoretic entropy, there was only log 2. But now, if we compute its topological entropy, then there is something that depends on the fiber. So it's different. And well,
So
in
there's
particular,
something which is bothering me a little bit.
okay.
How does this work with the variational principle? Because
Mhm.
it's only for a specific measure that it is log 2.
Yes, right. So it is log
Uh,
2, any measure which is a product of
of the two measures, then
the.
I see.
Yes. So it's a product of the uniform measure here and here any measure. But then the fact that here we have a topological entropy which is bigger tells you that these product measures are don't have like full entropy. There are other measures with more entropy. So, well, the fact that the topological entropy of the fiber makes a contribution here, which is strictly increasing, tells you that you don't need to apply the main theorem. I mean, you could, but you get the same thing as you would if you just computed the topological entropy of this. So if you want to distinguish S times T1 and S times T2 for T1 and T2 with different entropy, you can do it with topological entropy. But this may still be interesting if you want to distinguish products with zero entropy systems. So there so for instance, if you take T1 and T2 with low complexity, like different polynomial complexity, then slow entropy can distinguish these things. Which is interesting because there are other invariants that we know that don't work in these situations. I did not want to include too many things here, but we also know that we cannot make this conclusion with other specific invariants.
So just a question, even if you have positive entropy T1 and T2, and say both of them have the same entropy, isn't it possible that there's some weird scale that one can cook up which will distinguish T1 and T2? That you will have e to the power Tx, e to the power h times n, and then you have some weird prefactor which might distinguish the two.
Yes, well, I think that this is exactly what can happen here. So if T1 and T2 have zero entropy, then S times T1 and S
Right.
times T2 both have entropy log 2. But
Uh-huh.
there will be sub-exponential
Sub-exponential factor, which is
which comes from T, which could be like, I'm not sure, n squared, like polynomial, a polynomial quantity, which disappears in the exponential scale. But this exactly tells you that you can cook up weird scales that cancels the exponential contribution and captures the sub-exponential one. Yes. So now I want to make a brief description of the proof idea, very informally.
So Nicanor, it's kind of the R is up. Of course, we asked a lot of questions. I asked a lot of questions in between. I'm to blame, but what we can do is a couple of things. We can either take a small break and then get back to this, or we can continue. Like, if you think that it's 5-10 minutes, then we can just continue. There's no point of taking a break. But if you think it might take a little longer, then we can take a break and then come back to this in, like, say, 10 minutes or so.
Okay, no, I really think this should be like maybe at most 5 minutes. Like it's a very sketchy proof idea.
Okay, go ahead, Nicanor.
Okay, thanks. I will take at most 5 minutes. So This is just a notation thing. So for a topological system, for a finite set F of integers, this denotes the Bowen metric. So it's like the classical Bowen metric, which is indexed by a set F, which is an interval like from 0 to n. And this is the same thing, but for some arbitrary set of integers. And we have the same thing for this spanning number. So yes. Then, so what happens is we look at these Q products, and then we want to compute this number of n epsilon Bowen balls needed to cover the space, because this is the key quantity in the definition of zero entropy, and it also tells us what is the complexity of the system. So the thing is that this value is more or less approximately this quantity, which is the sum over the words in the language of the subshift y of the same spanning numbers in the fiber, but here they are indexed by the ranges of those words. So that is why we care about these ranges. And something that happens is that when the cocycle takes values between -1, 0, and 1, then these ranges are intervals, because so if you are a walker which makes steps that are either 1 or 0 or 1, then if you make 10 steps, the places you visit are an interval, right? If you make longer steps of length 3, then there will be holes that complicate things. But in this, let's assume that we are in this case because it's easier. So if this is true, then we can ignore the shape of these sets, and we only care about their cardinality. And from the definition of topological entropy, we have this estimate, which is that this spanning number of T, an interval of length n, is approximately exponential of the entropy of T times n, up to epsilon some lim subs, but well, let's just assume that this is more or less correct. So we can plug this estimate here, and we obtain that the relevant quantity is approximately the sum over the words in the language of length n of the exponential of the cardinality of the range times the entropy of the fiber.
So for instance, if it was like a Fulner, if you knew, for instance, that the range is essentially like a Fulner set, will it be still fine?
Yes, if they are not too far from being intervals, yes, it's essentially the same, but that requires some ugly computations. I may mention it if I have time.
Yeah, I'm just sort of thinking that instead of Z-valued cocycle, if you had a group-valued cocycle and this group was amenable acting on some space, then would something like this still work? Anyways.
I think it would work, but up to you need a lot of information of the shape of the ranges. That would be not necessarily Fellner sets, but you need to know how much invariant they are. And I believe that is what is the important thing. So if you know quantitatively how invariant are these sets, then you can like estimate these cardinalities or these quantities. So well, anyway, so here we have this quantity, which we know can be estimated as approximately this. So now the scale for the main theorem is this sum. So here we have an of t. So we sum over the words of length n, and we have the exponential of the range of those words times t, which is this parameter. So it is like exactly the same quantity, but instead of the topological entropy, we have the parameter T. And this scale has the property that the slow entropy of the product equals the topological entropy of T, because when T is smaller than the topological entropy, this whole quantity will be much smaller than this quantity here. Well, they are, I want to emphasize, they are the same thing, but here we have T and here we have entropy. So since this thing is monotone, one can kind of make some computations and prove that this one here is much smaller. And this one here is this spanning number. So remember that in the definition of slow entropy, we compared this quantity with the scale. So
And so your lambda condition essentially just ensures that since all you want is that lim sup or lim inf to be positive, if you have a lambda perturbation, then that doesn't, like if only lambda part of the space sees an interval of size C, you will still achieve this kind of a bound. Okay, I'm being very vague, but
yes, I think so. So, well,
yeah.
we want to compare these things. Now imagine that you have this, I think it is impossible, but imagine that you have a fold shift. So the language has cardinality 2 power n. And imagine that all words except one word have range 2. So the configurations would be periodic and these ranges would be bounded except for only one word. In that case, the cardinalities of these in that case, that kind of ruins the computation because you want well, if the range grows with n, then you can say that e power range times t is much bigger than e power range n times entropy. But if the range is bounded, I mean, for the word, like comparing individually these elements, not the sum, individually these ones with these ones. But for the words for which the range is bounded, then you don't get like limits as infinite or zero. I'm not sure if that was very clear, but
It helps.
okay. So, well, this proves that this scale has the property that the slow entropy is the entropy of T. And a last comment, which I think may be very related to your last question. So if tau takes values outside -1, 0, and 1, then this set's range can have holes, right? Can be sparse. And this sparseness, which is, well, I think it's good to think about sparseness as the opposite of invariance in the sense of the definition of Follner sequence. So this sparseness will cause extra growth of these quantities. For instance, if the range of a word is the first n even numbers, then this spanning number will be exponential of 2 times topological entropy times n. If we take the multiples of 3, here we will have a factor of 3. So there is like a rescaling. So one needs to quantify the extra contribution which is produced by the sparseness of these ranges. And it is possible, it works, and one can include it in the scale so that the things that you want to cancel out actually cancel out at that, and at the end you only get the topological entropy of the fiber system.
So for instance, what you are essentially saying is that if you are like a Fallner sequence, then you're in good shape. This is
Yes.
roughly what I'm reading.
Yes, I think it's exactly that. And if they are not, I mean,
So
even if they are.
then I guess if it's not, then all you care about is how the boundary is connected to the interior. And that should be, just the size of the boundary of the range divided by the size of the interior. And now you'll have to say that lambda proportion of your language realizes this. And okay. I don't
Yes,
know.
I think that's more or less true. So there should be a constant depending on how invariant or non-invariant is your set. And
Yeah.
I believe it should work more or less in a similar manner. So last comment. So obviously, after these results, a natural question that appears is if one can prove analogous results for measure-preserving systems, but using measure-theoretic zero-entropy, because the known results for measure-preserving systems are not proved using zero-entropy, they are proved using other things. And I am not sure, I think it could be true in some cases, but I know that the scales that are constructed here and that work for topological entropy of the fiber in general don't work. So in general, the scales that work for topological entropy grow much faster than what one would need, like
Wouldn't one somewhat use some kind of Jewett-Krieger theorem and find the minimal topological complexity of the embedding? Take your general measure preserving system, try to embed it in a topological system, and then take the minimal possible topological complexity of such a system. Okay. So, and then try to do the same kind of thing. Like then use your results, essentially. That's what I'm asking.
I'm
So-
not sure. It's like a good idea at least to try. I think it should be difficult, but I mean the proofs of the
Oh
measure
no,
theory.
definitely. I'm just
I
very shooting in the dark. But yeah.
Yeah, why not? Like, hopefully.
Anyways, we can talk about this after.
It's a good question, I think. So, yes. So, that's all from the talk. So, thanks a lot for listening.
Let's thank the speaker. Questions?
I am sure you made a comment on this throughout the talk, but I was just wondering if you could narrate this heuristic for me. If we have a system tau for which the lambda unboundedness is that lambda is very, very small. So there is very little proportion of orbits that are going outside, gets unbounded and goes out. So then in that case, how does the set RNW looks like? And then for such a system, what does the scale A look like?
So, for this system, the scale looks, I think, it still looks exactly like this. But I think it's good to think about, so take your favorite subshift with your favorite choice of tau with the property that the ranges grow. So for instance, maybe a Starman subshift or the subshift copy of the deterministic random walk where the ranges are unbounded for all words. So in that case, you have like uniform work of these numbers as n grows. Uniform in the sense that for all words, the range grow. Now take 100 copies of the same system. So take a disjoint union. And in the first one, you take your cocycle for which the range grows. And in the other ones, you take the constantly zero cocycle. So then you would have a sum of something. So you would have 100 copies of more or less the same words, but for 1% of them, you would have that these ranges grow as much as you want unboundedly. And for the others, they don't. But then when you make the quotient of this number, well, this spanning number over this spanning number, that it's not like you just get a factor of 1/100. It's a bit more complicated than that, but you can kind of manage to handle the quotient, and at the end the same thing happens. I'm not sure if that last part gives some actual intuition of what happens, but that is how the scale looks like, I think.
No, thanks. Especially the example is very fun to keep in head for that question. Thanks.
Thank you for the question.
Other questions? Okay, let's thank the speaker again for the wonderful talk.
Thanks a lot. Thanks for the questions and for the invitation. So